So if anyone is, works with sort of embedding models and is aware of OpenAI's latest embedding models, they train them with MRL. And this is a paper at NeurIPS 2022. And I'll also talk about a follow-up work that builds on top of MRL for web scale search. So get started. Oops. Okay, so this is what I was just talking about. So this late this January, OpenAI released new embedding models where they have support. Let me actually zoom in on this a bit. They mentioned that their new embedding models were trained with a technique that allows developers to basically shorten embeddings by just slicing off whichever part of the embedding you find useful. So why is this kind of shortening important? Especially for search, you can save a lot of memory in terms of storing the embedding. Instead of storing the full D-dimensional representation, you can store a much smaller version of it. You can improve search latency because smaller embeddings means faster search. And the more critical than just memory and time is that what if the largest embedding that you get from a large pre-trained foundation model just isn't the best for whatever task you have? And what does best even mean, right? So these are the kind of questions that motivated MRL. Okay, so as a really quick overview, when I talk about learned representations, this is what I mean. So typically we have some data in some modality, image, audio, text are common ones. Typically we pass these through some kind of deep featurizer. This could be a CNN transformer, vision transformer, whatever. And we get a D-dimensional real valued representation out of it. Typically these things can be 512, 2048 dimensional, and nowadays with some language models you can even get into like 15,000 and stuff like that. And typically when we're building a search system, you have a very large number of documents, and this can be nowadays, in the billions and the trillions of documents. And the data dimensionality is also, quite large. It's in the order of 10 to the power 2. So this is an n by d database, right? So n items, d dimensions. So these can get extremely large. And so the motivation here is query-based retrieval. So within this document, you have a query, and you want to look up, the most relevant items in your database for a given query. And so this is what's typically called nearest neighbor lookup. So yeah, this can be, you can do this for million-way classification as well. So you have a ton of labels. You can do instance level classification as well. So you're not classifying say 1,000 classes on ImageNet, you're classifying actual instances. So this can get, the label space can get really, really huge. So what are the challenges when you're actually trying to scale this up? So something that Google may do is that your databases are super huge, hundreds, maybe thousands of terabytes, and you have a linear dependence on your representation size D when you're searching, right? So typically a sort of easy search is something called a maximum inner product search. So you just take an inner product of your query with all the items in your database. And so that's just a simple matrix multiply. So it's order ND. So n, n rows, n items, and D columns are, data dimensionality. So it's linear in size D. And so that's super expensive to look up. You also require something called an approximate nearest neighbor search because at this scale, you cannot exhaustively search every single item in your database. You need to do some kind of intelligent pruning of your search space so you don't, you can find queries in a reasonable amount of time. So you need to typically you need to compress that index post hoc. You can't do it before because your data dimensionality that you get from your encoders is fixed. And combining these things together, that is to say they're incapable of multi-granularity. So if you want representations of a different size, you're kind of stuck with whatever encoder you're using, or you can use SVD or some kind of post hoc dimensionality reduction techniques if you want, but those typically don't work that well. Or and even worse, you could potentially retrain a model for whatever lower dimensionality you need, but that's super expensive at scale because these transformers are super compute hungry, data hungry, and it's just not at all scalable to keep training multiple models at different scales. And so typically what we do is use some kind of fixed 768 dimensional VIT for all our vision tasks. So today's talk, I'm going to be focusing on a specific aspect of tackling this problem, which is multi-fidelity representations. And by that, I mean, what if we can get a representation that can capture multiple scales or multiple fidelities or multiple granularities in one representation? And so if that's the case, then all we have to do is just slice that representation wherever we want, and we can use that for classification, retrieval, whatever downstream task we have. And this will also enable a sort of adaptive search, because you don't need to do any kind of post hoc compression and stuff to fit whatever database memory you can afford and things like that. So let's take a look at what exactly this means. From this. So the goal is to have one representation vector for all downstream tasks. So we don't need to do all of this post hoc compression or retraining. And we want to basically bake in this lower dimensional representations within a high dimensional embedding. And that's basically for free, because all we have to do is just slice it. So it's a constant time access of that embedding. And we also want these to be as accurate as independently trained counterparts, right? So if you have, say, a 2048 dimensional embedding, and you want, say you can only fit in 256 dimensions for your given database. So you would want whatever 256 dimensional embedding you get from this sort of one representation to be as good as if you had trained an independent model, right? You don't want the accuracy to drop too much, because then it's just not as useful. So you want to match those accuracies at all of these scales. And this turns out you can do a lot of interesting things if you have this, in terms of shortlisting and re-ranking for search problems, and I'll talk about that a little bit later. Okay, so let me talk about the actual method and what we actually do. So if you look at this sort of gray box here, that you can think of that as a latent embedding, Z 1 to D. So for example, for something like a ResNet 50, that D would be 2048. And typically what we do in supervised classification is to do some kind of ERM over this latent embedding 1 to D over, on ImageNet, say 1,000 classes, right? So you have 1,000 classes here, and you take a loss, typically a cross entropy loss at here. This LZ1 to D is a sort of default setup that you would do to, say, train ResNet 50 on ImageNet. So our method basically just makes a very simple modification. The backbone is fixed. The only modification is that we add this kind of aggregate loss. And so instead of taking just a default sort of vanilla loss at Z1 to D, we also take losses at these sort of logarithmically decaying scales, right? So that would be, on ResNet, for example, that would be, you take a loss at 2048 dimensions, and then the yellow one would be taking it at D by 2, so 1024 dimensions. The blue box would be taking a loss at 512 dimensions, and so on. And so you keep taking this sort of aggregate loss at multiple scales. And so intuitively, what this is trying to get the model to do is to say, okay, we want 1 to D to be a valid representation to do well on 1,000-way classification. We also want 1024 to do well. We also want 512 to do well, and so on, right? So it's sort of trying to get the model to say, okay, I need to learn a valid representation at all of these scales. And the Matryoshka name is basically, so if anyone has heard of Matryoshka dolls, there's this kind of Russian dolls that sort of fit inside each other. And so that was the sort of idea for the name. So you can think of these representations as these kind of dolls that are sort of fitting inside each other. So the red one is the smallest doll that fits inside the orange one, and the blue one, and so on. And so so what you can use this sort of learned representations for is you can do something like you take, instead of just searching with your biggest representation in gray, what you can do is shortlist a bunch of candidates with a smaller dimension, say the orange one, and then re-rank them with your full size embedding. And so this saves you a ton of cost, because you get a linear reduction in cost, which is just the size of the gray one divided by the size of the orange one. And I'll look at what these adaptive retrieval and classification things look like, but that's the basic idea behind MRL. Yes.
Like the white matrices, and you split them, all the white matrices, like what is exactly the
Yeah, that's a great question. So currently, this is not in the weight space. This is purely in the information bottleneck space, which is the only modification that we make to the actual architecture or loss is that typically after this stage, you'd have just a single n dot linear that projects you to, 1,000 classes on ImageNet and take a logistic, take the logits and take a cross entropy loss. So instead of that, we now have, 1, 2, 3, 4, 5 of those at different scales. So 5 different n dot linear heads, and you take a loss at all of those scales and just add them up together. So that's the modification. So it's not in the weight space. We don't do anything in the actual weight space.
In the input.
Yeah, so everything until the penultimate layer of your network, which is where you get the d-dimensional embedding that you then put all of your losses on. So everything until there is the exact same as a regular model.
Also, that's the output.
Yeah, so this is so Z1 to D here is the penultimate layer. So it's the output representation. So this is basically what you can think of as an encoding for data. So if you want to just encode your data, this is what you would get out of it. So now if you learn if you learn your model in this way, your encoding that you get can now just be sliced at these different scales to get smaller embeddings.
So there is like just let's say the 10 first.
Yeah, exactly. So the idea is like, so the idea was like, instead of training all of these different models separately to get this, or even worse, to try and do some kind of dimensionality reduction on the biggest one to get smaller ones after the fact, you can just learn all of them at once. That's the idea.
I have one quick question.
Yeah.
Can you like train a pre-trained model for dimensionality and just add different one layer projector for different representation scale?
Yeah, you can fine tune this kind of behavior as well. Like you don't need to, you can take a pre-trained model and then just add a bunch of heads at different scales and then take the loss at each scale. And it will sort of reshape the learned embeddings into this kind of like nested structure.
For example, you have a 48 dimensionality, and then you just train a projector with your smaller dimensionality and use that kind of output as a penultimate layer. So we don't need to combine everything together.
I mean, that's essentially what we are doing. Like we have different sizes of projectors after this, which is where we're taking the loss on. So the representation itself is fixed because we want it to be fixed so that we only have to do one inference pass to get it at the end. So we don't have any additional inference cost because the idea is like, we don't want to have, we have these like sort of sub models baked into a single model, but we don't want to, during inference, have to do 8 different inference passes over each of them. So we just have one inference, and the way we get the different representations is just slice them. So that was the idea. Yeah. Any other questions about the method? Because this is sort of the only thing that's behind the method. It's a super simple modification in the representation bottleneck space, so the embedding space. Yeah.
The tasks, what is like the idea is that sometimes I want to classify 10 things and then 20 things.
Yeah, so I mean, the setup I'm talking about here is a supervised classification setup. So it's like, you can think of this as like ImageNet classification or something, but it's applicable anywhere. Like we showed this on a contrastive learning setup with Align at Google. So it's really applicable to anywhere where you would need to learn a dense representation. So that could be classification. We also show it for retrieval. I'll talk about some of the tasks later on. Yeah.
So in this case, all the heads are kind of doing the same task. The task is the same across all the.
When you say the task is the same, can you?
You're using different sizes of these embeddings to ImageNet classification, but all the classes. But
yes, the task is the same. The goal is the same. So again, this structure is the exact same. So this 2048 dimensional embedding is the exact same as the vanilla model. What we're doing is adding a bunch of, there's 2 different ways you can do it. You can either add independent heads at the end of this at different scales to project these to, D over 16, D over 8, and so on. Get all the 1,000 logits, take your cross entropy loss and just sum them all together. You could potentially weight those differently. So we did that. We tried weighting the lower losses a little bit higher to see if we can boost those numbers, and that worked. But it sort of reduced some of the performance at intermediate dimensionalities, which makes sense because it's just harder to do well at really small compression scales. So there's a ton of things you can do, but this is the sort of simplest thing, which is just add a head at each scale, compute get the logits, get the loss, and then just add them all up together.
But there's no weighting. It's like
You can do with that, but the default setup that we did in all our experiments is no weighting, no hyperparameter tuning, nothing. Like the nice, I think personally, I think one of the nice things about this work is that it just requires very little overhead to get good performance, is what we found typically.
Like, did you guys think about like, because the shorter embedding may be better for like high level features, so I think about using it for a task that had like higher level classes, for instance, like ImageNet has like hierarchy.
Yes.
You can use this to do.
Yeah, that's a great question. We actually did check that out, and it turns out, how large do you think of an embedding you need to do well on ImageNet? Like 2048, for example, will get you something like 75% accuracy with ResNet. So I'll talk about that, what that looks like. Yeah, great question. Okay, let me move on. So this is exactly what I was just talking about here, where so we have these heads at different scales, and we take a loss at each scale and then just add them up together. So this is the entire method for supervised classification. Yeah. Okay. So this is a nice visualization from a recent Hugging Face blog on sentence transformers. So this is just gonna play this. So it's essentially exactly what it is. So you have some kind of query that goes in, whether it's so nice, into some kind of language model. You get your default embedding size, and then you just truncate it to whatever you want for whatever task at hand.
How do you choose how do you select the dimensionality?
So the dimensionalities for training were chosen at logarithmic scales, because we observed that if you train independent models, the accuracy scales logarithmically. So that's why we chose that. And I'll show you what that looks like in a sec, in terms of the accuracy. So as a quick summary, we're solving the same task at multiple log D granularities. You can apply this to any representation learning setup. We did contrastive learning with a line. We did BERT, mass language modeling, multimodal stuff. And it also scales with ease. So we scaled this from ImageNet all the way up to JFT, which is Google's internal billion scale dataset. And like I said, the first K dimensions form the required low dimensional embedding. So you just slice off whatever you need. Yeah.
So basically, you have a trained model already, and you
Yeah.
just like in the last layer, linear matrices.
Yeah.
You train this.
Yeah.
Is that correct?
Basically.
The rest is from.
Yes. So we don't do this on pre-trained models. We actually train these from scratch in the things that we're showing, but you can do it for pre-trained models too. There's nothing to say. And we tried that to see like how, like if we fine tune with this kind of loss, like how much can we get close to training from scratch and things like that. So we have some of those observations as well.
Like, let's say that I train this matrices independently for
Yeah.
1,000 models.
Yeah.
And then I just, select which matrix I want to have.
Yeah.
How is that different?
Yeah, that's a great question. So logically, it's no different whatsoever. But it is, I mean, it's much more expensive to do because you have to train, say 10 models at different scales.
No, but pre-trained model.
Yeah.
Train.
Yeah.
And then you just train the extra matrix you append at the end.
Right.
Like, so you only train in the one matrix. You don't
Yeah.
train the rest of the
You can do that too. We tried that as well. We tried just freezing the backbone and just training the weights, and that just doesn't, it just doesn't do well enough. You need some non-linearities to train well. It doesn't converge to good performance, basically. You don't need to train the entire network. So what we tried is to successively unfreeze more and more non-linearities and see like how much do we need to unfreeze and fine tune over to get decent performance at lower dimensionalities. So we have a whole ablation on that in the paper. Yeah.
And what's the difference with your method? Like, what exactly do you say in terms of training time?
So the nice thing is that there is no training time overhead over a normal method because it's just one model. And there's a very minimal parameter. The only parameters that we're adding are like a couple more NN linears at the very end. So it's adding maybe like 0.2% parameters to the model. And we also do no hyperparameter tuning whatsoever. So if you do that, you could probably get even better. So let me just move on to the actual numbers. I'll talk about the application. So I'm going to discuss classification and retrieval in a sec, and to show how this technique actually performs And so the setup is I'm gonna talk about ResNet 50 on ImageNet, so super standard academia sort of setup. And this work was in collaboration with Google, so they were able to run stuff like training a VIT from scratch on JFT, and also Align, which is a multimodal vision plus language technique. So it's a VIT B16 encoder and BERT-based language encoder. And I'm going to talk about both one versus all accuracy, which is this sort of standard setup, and one nearest neighbor retrieval. And I'll also talk about adaptive classification. Okay, so this is the main results. So what you can see here is top one accuracy on ImageNet versus the representation size. So 2048 is the sort of default that you get from ResNet. The green line that you can see in this plot are independently trained models at each scale. So we trained 9 independent models from scratch at each of these scales. And the blue line is a single model that's been evaluated at each of these scales. So as you can see, at lower dimensionalities, our single model actually outperforms independently trained models. And you can think of that as because it's getting some kind of supervision from losses at higher scales. And so it's actually able to do better at smaller scales. It's not able to just match it, but it's actually able to do better. And the orange line that you can see here is something we call MRL-E, where E stands for efficient. So the efficiency there is just to do, instead of having multiple heads at each embedding, at each representation size, you can just have a single one and do weight tying across all of them. And that can add some parameter efficiency. But that you then suffer a little bit because you lose that sort of sense of independence of heads. And we also showed stuff like, well, these last 3 methods here are dimensionality reduction techniques, which do kind of okay at higher representation sizes, but then drop off really badly later on, right? So if you have an application where you want a 32-dimensional embedding for your task, these things will not do well. You're going to drop off from 75% accuracy to like something in the 40s and 50s.
Do you need more training equals in order to reach a similar performance as that?
More training, what, sorry?
More training equals or equal?
No, so we replicated the exact same setup to train these independent models as we did for our model.
Yeah, and I guess your training time should be less, right? Because your embedding side is a mix of small values.
On average, we didn't find it to be that different, actually, for different scales. Yeah, because
so the main computation time comes from the backbone.
Yeah, because the backbone is the same for everything. It's just the final sort of projection head that's different in each case. Yeah, good question. Yeah. Okay.
I have another question.
Yeah.
So for SVD here, you just use backbone together, like the representation of the backbone, and then perform SVD together, like the height.
Yeah, right. Yeah, that's a great question. So SVD here is on the highest dimensional embedding, which is 2048. So we run SVD on the embeddings and then do a lookup there. Yeah.
Do you have an interpretation why your method outperforms SVD, or like in other words, why SVD doesn't work well in this case?
I mean, so SVD does okay for higher. So it's just that I think it's just not able to capture like if you compress it down to 32 components, it's just losing all sense of the variance at that scale. Like it's just too much compression, basically, is the intuition for SVD to do well. Yeah.
Did you try training with low rank things, like not doing SVD in initial representation, but other training? Low rank representation?
Not at this time. No, we didn't try that out. Yeah, we didn't try enforcing low rankness in
that's what I meant before, whether you can train your model and then train on top of this low rank representation.
We didn't do that explicitly in the sense of like LoRa kind of things, but
Sorry, it's like instead of training all together, you train one model,
right,
and then you train on top its adapter independently. Like,
right. So you freeze the backbone and train heads. Yeah, we did do that. Yeah, we tried that.
Where does that stop?
Those, I don't think I have those results here, but those are in the main paper in the appendix. But they basically don't do super well if you don't unfreeze some of the backbone, because it's just very hard to adapt a frozen backbone to purely in the information space. Oh, I see. I think it's slightly better than SVD at lower embedding sizes, but it's yeah, because you still do have this kind of information that's learned across multiple scales. It's just hard to align them when the backbone is frozen. Yeah.
So, Aniket, have you tried multi-layer projectors instead of just one layer?
No, we didn't. We didn't find a need to do that. But you can definitely do that. And in fact, there's follow-up work after this that does MRL in the weight space of the transformer. So I'm not going to talk about that today because I didn't work on that. But that's the sort of next step, which is to say, can you do this in like the MLPs of a transformer? And so you can like slice off sub-transformers within a transformer, for example. So I'm not going to talk about that sort of side of it, but here it's just a single layer because it's the simplest thing and it's just what worked sort of reasonably well. Yeah, so here, these are the results at scale. So these are on JFT and Align. So these are huge data sets. JFT is, I think, it's like 1 point something billion, or might be more. It's in the billions of examples. These are both internal Google data sets. And so the finding that we had is that this scales to 1 billion images without accuracy drop. So here you can see the blue and green lines are the sort of same thing. So it's a model trained on GFT, a VIT model trained on GFT. And unfortunately, Google was not okay with us training like these many independent models on GFT to test this out. So we don't have the sort of, the FF baseline here because it was just way too expensive. So, the only thing that you could reasonably compare this to was to do, random projections on top of pre-trained models. Because it's just, even practically, that's the only thing you can actually do. And so we did much better than these baselines. Okay, and this is probably one of the more interesting takeaways from MRL, which is to say, we trained things at very specific scales. So these logarithmic scales, 8, 16, 32, and so on. And so it's not immediately clear whether, what happens if you want a representation somewhere in the middle. Like what happens if we are training at 256 and 512, but you can only fit 384, right? But you didn't explicitly train at that scale. And so what we found is that the accuracy actually interpolates pretty smoothly between scales. So what you can do is you can just essentially just freely slice off whatever embedding size you want and it will work. And so this is really nice because it means that our method isn't super sensitive to the granularities at which you train, as long as they're reasonably well spaced, and you can freely slice off things at whatever size you want, and you can have super fine-grained deployment. So does this make sense? This is basically what allows us to just slice things off wherever we want and use it for free, basically. And this worked at both, ImageNet scales. You can see in the purple. So the purple. So if you look at the sort of line at the top, the purple things are the dimensionalities we actually trained on, and the red points are basically we didn't train there, but we're just evaluating there, and the accuracy is right in the middle of both. Okay, so yeah, this is something. So after OpenAI released their latest models, people were kind of curious as to why these things seem to work well, and so there was a lot of really nice follow-up work that was posted on Twitter. So this is one of them. So what this is showing is PCA on MRL embeddings from OpenAI's embedding model. And so the visualization that you see here is that you're increasing the dimensionality on which you're doing PCA to 3 dimensions, to 3 principal components. And what you can see is that initially, as you have very small dimensions, so I'm going to wait for that to get smaller again. Yeah, so you can see that there's more change and a little bit more of jitter in the representations. But once you hit around 500, the sort of structure stabilizes somewhat, and there's not a ton of change. So that's one kind of intuition, which is that, you can capture a reasonable amount of structure of data in lower embeddings, in a lower dimensional space. And to capture some of the more sort of nuances of the individual instances is when you would need to increase your data dimensionality, right? So you can think of this as you probably don't need, 3072 dimensions for a, cat versus dog classifier. But if you would want to classify specific species of cats or specific species of dogs, maybe you need to increase your complexity or your embedding size a little bit. So this is one of the sort of intuitions, and there's some more stuff that I won't talk about here, just in the interest of time. But I've written about that in this blog post that I have, talking about t-SNE and some other sort of visualizations. But this is sort of one sort of intuition behind sort of capturing low dimensional structure. Okay, I'm going to quickly go through this. So this is a very simple method that we did, which is to say, we're going to start off classifying ImageNet with 8 dimensions. So the smallest thing that we have, and we're going to have a holdout set where we decide, how uncertain do we have to be before we decide, okay, this 8 dimensions is not enough, I'm going to jump to 16. And so we learn thresholds at each of these stages and say, okay, 8 dimensions can do well enough on, perhaps 60% of the data. And for the rest, it's not enough. So we jump up to 8, and then we jump up to 16, and then 16 does well on maybe another 60% of that data. And then we jump up to 32 and so on. So this is super useful because you don't have to, you don't have to know ahead of time what the best size is, and you can just sort of learn this. This is a sort of very simple method to do that. And what we found is that if you do this kind of adaptive classification, you can match the accuracy of independent models for a much smaller representation size. And so this is a sort of automated way of just, running a, yes.
Yeah, I'm not sure how do you automatically so what's your criteria or what's your do you have something like store box or some loop?
Yeah, that's a good question. So basically what we do is you create some subset, some holdout set of your data to learn the thresholds. And the way I think that we learned thresholds was just to, I think all we looked at was the score function in that case was just the softmax scores, basically.
So you use the validation set, right?
No, it wasn't the validation set. We created some subset of the training set to do this. So I think we use like a 50K subset of ImageNet to learn the thresholds, and then we evaluated on the rest of it. So we evaluated these things.
You actually train a network to predict.
No. We didn't train a network. We just inferred those samples and saw what the uncertainty was with the softmax scores. And then with 8 dimensions, if we have a majority of samples that are uncertain, so there were some thresholds for that, then we jump up to 16. And then we learn a new threshold on 16, and then we jump up to 32 and so on.
Yeah, but I think at that time, the problem with pure sample, right? For example, in ImageNet, at that time, the image comes to you one by one. Then how to decide the threshold for a single image?
Oh, the thresholds are decided ahead of time and then fixed. And so then they're just used for inference going forward. So there's 2 stages. First you learn the thresholds, then fix them, and then you do the inference. So these results are after we learn and fix the thresholds. Yeah. So this is basically just the simplest thing we could have possibly done to automate the process of running this. Yeah.
So here you just already learned those representation, and you just to choose which representation to use, right?
Yeah.
But why we have this curve which is different before? Because we are still just use the representation size and then to compute accuracy. Why? I thought adaptive classification is for choosing the good representation size, right? Why we have different curve?
Yeah. So it's essentially trying to abstract away having to choose a size. So it's sort of the adaptivity is trying to say how much marginal utility do we need over our lowest embedding to correctly be able to classify something that the lower one failed at. So 8, for example, 8 dimensions is the lowest size that we have. It will be able to do well. So I think on ImageNet, 8 dimensions can classify 65% of the examples correctly. So there's a 10% gap with the highest one. And so then we decide, okay, on these remaining ones that we can't do well, we're going to jump up to 16. So it's trying to say how much utility can we add with adding additional 8 embeddings on top of the previous 8 to do better than 8 can. So this is trying all this is trying to do is decide when do we make that jump from 8 to 16. So we infer an example and we compute some score on it, and we find that, oh, it's less than the threshold for 8. So we're going to jump to 16. And then say that it's less than the threshold for 16. Oh, then we'll jump to 32. And so we'll keep jumping up until we cross the threshold. And if we fail all of them, then we'll just use 2048, for example. Yeah. And so actually, if you do this, you can actually compute the average embedding size that you need to do well. So does anyone have any guesses what that might be? Like it's somewhere between 8 and 2048. So if you basically the setup is like if you run this on each sample in your test set, each of them will require a different embedding size. The first embedding size that does well. So if you average that embedding size over all your test data, like what do you think that might be? Any guesses? Any rough guesses? It's from 8 to 24. Do you think it's high? Do you think it's low? 32 would be super. It's not quite that low. That would have been pretty cool. It's something like 50 or 60. But that's also pretty huge, right? Because like ResNet is a pretty popular benchmark based on an ImageNet, and it's using 2048 dimensional embeddings. But the average that you need to do well on is only like 60. That's a huge compression, right? So that's just another sort of factor that tells you probably don't need to be using these sort of huge representation sizes. Okay.
Quick question.
Yeah.
Is this for inference or for training? Like the adaptive classification?
I mean, you learn the thresholds with some kind of, I mean, you sort of train or learn thresholds with a holdout set of the train set, but I mean, this is an inference test, but like this is just checking like what your test accuracy would be after you do this.
But during inference, if you wanted to know what the ideal size would be, then would you need to like do inference on each of the samples until you find the one that's best fits your input? Because I thought the idea was that during inference, you only need to like pass it through one of the granularities, right?
Yeah, so you only need to do inference once. It's just that you compute your score or your uncertainty at 8, and then decide, oh, this is not enough. Like this uncertainty is too high, so we're going to go to 16. And then if that is over the threshold, then we stop there. If it's under the threshold, we go to 32 or we go to 64 and so on. We keep increasing like if we think that we're still too uncertain, we keep increasing the dimensionality until we think, okay, we're not that uncertain anymore and we can stop here.
Oh, but so you're computing uncertainty with a very like lightweight model or a function?
It's not a model, it's just the softmax score.
Okay.
Yeah, you could learn like a model to do that, but like softmax is like a trivial sort of way to do it.
Okay, thank you.
Yeah.
So just a plan again, so this isn't offering any like efficiency benefits, right? This is just
to see if you can, this is just a thing to like automate this process. Yeah. Okay. So retrieval, okay, I'm just going to go a little bit quickly over this, but retrieval is basically just finding the most relevant images in a database, and it's evaluated using something called mean average precision. I'm not going to go into what this exactly is, but it's just a measure of at different scales of K, which is how many neighbors you retrieve, how well do we do on average when we're retrieving, say, 10 neighbors with, K, a short list of K. So these are the kind of numbers. So these graphs will look very familiar. So this is, blue is MRL, green is independently trained models, and so on. So this is a very similar finding on this different metric compared to our top one, our simple top one. So this is a measure of how well we can do, how well we can retrieve things at different scales on ImageNet, and we can do better than independently trained models again. So this is just very similar to the findings on classification. And now this is a sort of interesting sort of actual real world application of MRL, which is adaptive retrieval. So remember we started off with this huge database N by D. And so now instead of just searching with our entire gray one here, which is, a matrix product with, say 2048 embeddings, what we can do is instead we use the smallest one that we have, which is 8. And so you get a linear, reduction in cost, right? And then what you can do is re-rank that to get the top 200 documents, and then use, say some slightly larger embedding to do that re-ranking. And so this sort of shortlist with low and re-rank with high is a sort of hack that you can do to abstract away the cost of having to, do the entire matrix multiply at the largest scale. And so you can very clearly see that there's a huge reduction in cost because M here typically is like M is 200 and N here is like 50,000, right, on ImageNet, or it can be much, much larger. And DS is also, quite small. Yeah, and then this is basically how you just get your final shortlist from which you get your 10 nearest neighbors, 20 nearest neighbors, whatever. So these are some of the numbers that we got. So this is a little bit, this is quite a dense graph, but our takeaways from doing this is if we just look at various combinations of dimensionalities to shortlist and then re-rank, we can get for the same MAP numbers on ImageNet, we're looking now at megaflops per query. So for a given query, how many megaflops do we need to do the retrieval? And that depends basically on the size of your embedding and the size of your search space. And we found both substantial theoretical and real world speed ups for doing this sort of simple shortlist re-rank thing. Because the intuition again here is you're capturing some kind of lower dimensional structure for free within a larger embedding. So doing shortlisting and then re-ranking is pretty cheap, and it works quite well. This is also a very well-known technique in the search community of doing the shortlist re-rank thing. This is just now we can just do it with one embedding instead of having to do it with different ones. And this is the same thing on a larger sort of data set that we constructed to check this out, but we observed similar trends with just different constants in terms of the actual speedups that we got. And we also have this thing called funnel retrieval, which is basically another sort of simple automating thing that we do, which is to successively so we start off with a large short list and a low dimension, and then we sort of increase the dimension and decrease the short list, and then increase the dimension and then decrease the short list. And so we're sort of successively refining the documents at each stage. And so it kind of looks like a funnel. And so that's what that is. And so that, again, abstracts the need for you as the designer of the system to decide what is the best DS, what is the best DR. You're just going to start with the lowest one in a large short list and then just keep going lower and lower. And that also does, pretty well. You can get pretty good, you can match the accuracy of much, heavier computation and much lower computation here. Okay, and this is an application from Zenova that shows this. So, there's a query, what is a panda, and there's some text here, and they're showing that, the stability of your results is, pretty high as you decrease your embedding dimensionality. So the top result, which is a panda as a large black and white bear native to China, it stays the top result even if you decrease the embedding size from 768, I think, to 64, all the way down to 64. So it's showing that doing this kind of adaptive retrieval is pretty powerful. It can get pretty good results. Okay, so now the question is, why can't we just do this? Like, why can't Google just do this for free? Because what if they train a JFT, if they train a VIT on JFT at Google, why can't they just use this technique to serve Google search? So the problem is that every query here has a different shortlist, right? So you have, if you remember, like a 200 shortlist. That shortlist will be different for every query that you get, right? Because those samples will be different. And you also need to build so ANNS here stands for Approximate Nearest Neighbor Search. So that's basically a search system that is not exhaustively searching everything. Because this is required because at Google scales, that shortlist is not going to be 200. It's going to be like 100,000. So again, you don't want to be searching these things exhaustively. And so it's very hard. This presents a lot of system challenges to build these things that are constantly changing and constantly adapting to different sizes and different actual items. So indexing these things is very hard. And so that's where the second work that I'm going to be talking about relatively briefly today comes in. So this is a framework that builds on top of MRL, the sort of adaptivity that MRL provides to power flexible semantic search. So if you want to build a search system on a vector database, this is trying to do that in a sort of flexible, decoupled way. Okay, so there's two structures that I'm going to focus on here. So if you think about, how do you actually search approximately? So there's two primary ways. One is to prune the search space. So we're saying we're not going to search the entire matrix. We're going to search some subset of that space. And the second technique is to actually search more efficiently. So when you're actually computing distances from your query to all of your items, you're going to compute the distances more efficiently. So these are the two ways you can sort of speed up your search. So this is doing the search space pruning. So if you have, say, 1 billion points that you're searching over, the sort of regular technique would be you cluster those 1 billion points into, say, 50,000 clusters. This is, I think, actually the actual numbers at Google, but don't tell anyone. So this is 128 dimensional embeddings, and then what you do is you have another step here where you have more clusters again, so it's a hierarchical tree. And then you do a scan within that for a query. So basically what happens is, for a given query, you first check what is its nearest 50K cluster, or maybe its nearest 5 50K clusters. And then within those clusters, you see which are the nearest clusters again, because these clusters are basically just represented by centroids. So you're just computing centroid distances. And then within the last sort of candidate that you have, you do a linear scan. You do an exhaustive search. So instead of doing a linear scan in the billion points, you're doing it only in a very small sort of subset of points. And so that's where your speed up is coming from. But then the question is like, what if you pick the wrong clusters? Like, what if you miss some clusters, right? That's the sort of classic example of where approximate search can go wrong. And so what you notice here is that the dimensionality that you need to use at each of these stages is the same because you only have one embedding. But with something like MRL, you can actually use different sizes of embeddings at each of these stages. So what you can do is, instead of using 50K clusters, you can decrease the dimensionality by 2 and then increase the number of clusters by 2 for the same cost, right? Because if you think about it, it's just you're doing a matrix multiply with 100 centroids and 32 dimensions, or 50K centroids and 128 dimensions. So it's the same cost. And so you can basically add a bit more granularity in terms of the centroid structure that you have, because we saw that going from 128 to 64 preserves a ton of the accuracy, and you're now doubling the number of clusters you can index. And then you can again do a linear scan with your highest size again. And so you can sort of decouple the embedding size that you need at each of these stages. And so that's basically what this framework lets you do. The second thing I'm going to talk about, this is super dense. Apologize, but basically this is a technique. This is basically the status quo technique for doing quantization for search systems, which is called product quantization. So if you think of regular quantization, you have, say a 128 dimensional embedding. You're going to say, I'm going to quantize this to say 8 bits or 16 bits or whatever, right? So you're quantizing the entire representation to 16 bits. What product quantization does is that it first splits your entire embedding into multiple chunks. So here you can see the 128 dimensional embedding is split into 8 chunks. And now what they're going to do is learn a clustering structure on each column of this matrix here, and then represent those things as centroids. So if you learn 256 clusters, that's 8 bits. So you can represent the data point by its nearest centroid, which is now just an 8-bit number instead of whatever, a 1024 by 32-bit floating point number. So you get a huge level of compression by doing this. And then during search, for whatever query you have, you can construct a basic lookup table with the distances of all of these centroids, right? So this is way smaller. You're going from 50K to only 256. And then you just find the distance for all of the database vectors that you have and sort them by distances. And then what you can do is just add up all of those distances here, and then you get your final distance. So basically, this is just a way to substantially reduce the cost of your distance computation when you're doing search. So this is another technique that we looked at. So we looked at both components of search. Search space pruning with the IVF, the hierarchical tree structure, and cheap distance computation with product quantization.
So is it the same as residual quantization?
It's very similar to residual quantization, yeah. Okay, so these are the numbers that we got. So here now on the left side, we have top 1 accuracy on ImageNet retrieval. So ImageNet retrieval is the same problem that we just saw in MRL. And now, instead of doing retrieval with an exact search, because on ImageNet, you can afford exact search because it's not that huge. But anything larger than ImageNet, you really cannot sort of store those indices in your memory at all. And so you build these tree structures. So rigid IVF here is just building a tree structure with rigid embedding, so not MRL embeddings. And AdANNS here is to build that kind of decoupled structure. And so what we saw is that the search latency per query here is actual real-world search latency. And so we saw that to match the same 70% accuracy, we can have something like a 90 times speed up over IVF, purely from the sort of structure that we can enforce, or we can decouple the embedding sizes that we need. And for the same search latency, we can also get a pretty good accuracy bump, especially at super low search latencies, which is typically what we care about anyway. So that's the left plot. The right plot is looking at OPQ. So this is a sort of variant of product quantization, and we're doing this on natural questions, which is a large passage retrieval database. And so here now we have, instead of looking at search latency, we're looking at compute budget, because when you do quantization, you quantize to some number of bits. And so on the x-axis, you have, you're quantizing your representation to 96 bytes or 32 bytes and so on. And so we saw that doing this with AdANNS, you can get, pretty good bumps on both size of your embedding and accuracy. So this is actually quite huge because you can use, instead of using a 64-dimensional, instead of encoding your database to 64 bytes, you can freely encode it to 32 bytes for the same accuracy. So which means you're halving your database storage cost for free. Or if you don't care too much about your database storage cost, you can also just get a really nice accuracy bump if you bump up to 48 or 64 bytes on natural questions. So this, AdANNS typically, it seems to work pretty well for both stages of search, is what we observed. And this is a bit more of an extensive evaluation where we have a bunch more baselines. So we played around with, so I'll talk about maybe a few of them really quick. The MGIVFRR. So these are quite dense in terms of the naming, but you can think of the MGIVFR, which is in green, as a very strong baseline where we took independently trained models, learned independent tree indices on each of them, and then sort of like added the adaptivity by doing inference over each of these things and then picking the best one at each stage. So it's sort of replicating the setup of AdANNS, but the problem is that it's way more expensive to actually run it because you have to do multiple inferences, you have to build multiple indices, you have to train multiple models. So it just amplifies the cost at each stage. But we wanted to see, okay, we can, it's super expensive. We're not actually going to use it, but let's see how well it does. And it turns out we can actually do even better than even this like pretty strong baseline as well. And then the black one is just doing that with SVD. So again, typically does not work super well. And the baselines in red and purple are just non-adaptive, completely like standard setups for learning trees on MR is just Matryoshka representations, and RR is just the default FF stuff that we saw earlier. And so the takeaway from this is that we tried out a bunch of baselines that we thought were pretty powerful, and we can still do reasonably well compared to matching their accuracy at the same number of flops per query. Yeah.
I'm keep thinking about why like SVD obviously can't work well in deep learning environment. So I'm wondering whether it's because the deep environment, they don't follow such high frequency, low frequency pattern. Because if it follows this pattern, then it can automatically do that much.
Yeah, that's a good question. I think that the thing is that if you look at the actual, if you run a PCA on it and you actually check the sort of variance ratio, the sort of explainable variance of different dimensions, you would ideally want a lot of your variance ratio to be explained in the sort of first few bits, but that doesn't, it's actually kind of diffused across everything if you don't train it with MRL. And so the problem is like, if you slice off half of it, the performance is going to decrease by half because you're cutting off like half of the explainable variance sort of. That's the sort of intuition. Does that make sense? So like if you look at how much variance is captured by each principal component,
yes,
it's like almost a uniform distribution over the embeddings. So like each embedding is adding almost the same amount of information, whereas in MRL we're trying to pack that more in the beginning.
okay.
So that's the intuition.
Yes, so the criteria of GCO actually is different, which is how to treat the variance.
Yeah, that's one thing. And another sort of more hand-wavy thing is just that SVD and PCA are like they're not data-driven compression. And MRL is like data-driven compression because we're learning the compression. That's a little bit more of a kind of hand-wavy explanation, but it is more flexible because you're not adding your like inductive bias of saying, oh, we want the variance to be captured in these directions and so on. So that's one more reason that but yeah, great question. MRL plus adding MRL to the existing ANNS structure is where we come up with AdANNS. And so our takeaway from this work was that MRL representations just seem to compress things better than rigid embeddings because of the way that we're packing that information. And we found that this works across data structures. So I didn't talk about it here, but we also showed this on Meta's HNSW structure, which is a big hierarchical graph. We showed it on Google's, which is IVF. We also showed it on Microsoft's graph-based structure called disk-ANN, which does a really interesting thing of trying to hybridize an index across SSDs and RAM. So there's just too many things to talk about in this work. But if you're interested in semantic search and search structures, I recommend you to check out the paper. We found that for clustering, we can get really good benefits for substantially less compute. And we can also touch more data points with flexibility, which just means that you can decrease your embedding size and just look at more clusters, right? Which is nice because you're just looking for more. You can potentially find more diverse candidates that way. And then the takeaway here is that your highest dimensionality might not be the best for a quantization budget. So this is what we found, which is that if you decide to quantize to 32 bytes, we found that quantizing with the largest embedding size that you have is not actually the best. So if you take an MRL embedding of 2048 and compress to 32, that actually does worse than if you compress it from, say, 256 or from 128, which means that, typically, if you were building this with a rigid system, the only thing you have is the 2048 embedding. And so you're sort of stuck doing quantization on 2048. But if you have MRL, you can quantize to 32 from any size for free. And so we found that actually gives you a reasonably good performance boost as well. And that optimal dimensionality to do that can be found with MRL by slicing. You do have to do some like search over, to find which one actually works well, but you don't need to train multiple models or do dimensionality reduction techniques. Okay, and so yeah, so in conclusion, I presented MRL, which is a fairly general purpose representation learning paradigm that we found to be fairly agnostic to scale. So we tested ImageNet scale and JFT scale, task, classification, retrieval, and modality. So we tested this for vision, language, and vision plus language, contrastive learning. We also found that we can have these kind of multi-granular databases at web scale for free. And these kind of techniques are complementary to existing techniques because all we're changing is the embedding. And so anything that uses embeddings, you just replace it with our embeddings and you can do more interesting things. That's the sort of takeaway. And then all of this results in fast, but still pretty accurate classification and retrieval at web scale. So this is basically what someone like Google would be using and is using. So yeah, if anyone wants some more information, I have a blog post that talks about a lot more of the specifics of representation learning, some of the reasons why we actually thought of creating MRL in the first place, why it works, which I gave a little teaser on with that PCA visualization. And then if any of you want to use MRL, why you would want to use it and how you can use it. And yeah, please feel free to get in touch with me on email or on my Twitter. And yeah, that's pretty much it. If anyone has any more questions, I'd be happy to answer.
For the free talk, actually, I have one question. So
Yeah.
for the MRL paper, so you just, so you are, in addition to original representation embedding, and you add extra dimension for the larger representation, right? So have you ever tried to visualize those additional dimensions to see what you are adding after you increasing the?
Yeah, that's a great question. Let me go on to some of this. Yeah, so we did try this, like visualizing this stuff with GradCam. So ImageNet has this kind of word net hierarchy. So it has like this superclass and subclass structure. So if you look at this second image here, the ground truth of this image is a rock python, and the prediction for 8 dimensions is boa constrictor. So it's not able to predict it correctly with the lowest size. But as soon as we jump to 16, then it's then stable all the way to 2048, and it correctly predicts rock python. So the GradCam map here is not super indicative of why this is happening. But if you look up here, this is a little bit more clear. So the ground truth here, like, I don't know, if you ask me what the ground truth, like what I would classify this image as, I don't know if I would say plastic bag, but I probably wouldn't say shower cap. But anyway, so 8 dimensions thinks it's a shower cap, and you can see it's looking a little bit more at the gradients are a little bit more active at the head of this person, and so it thinks it's a shower cap. But as soon as you increase the embedding size, it sort of ignores that and starts focusing on the plastic bag. So we have some more of these kind of visualizations in the paper, and the intuition is that lower dimensional embeddings can capture sort of superclass structures. So it knows that this is a snake at 8 dimensions. It just doesn't know what kind of snake. So you need to sort of increase the embedding size until it can correctly decide, oh, this isn't a boa constrictor, this is probably a rock python or something like that. Yeah.
And for the 2048
Yeah.
image, I feel like it pay less attention to the shadow cap. So
Yeah.
I feel like it is, but it looks like it's removing information instead of adding more information for the image.
Remove by what sorry, what do you mean by removing information?
Yeah,
Like,
I feel like it focuses more on the plastic bag, but
yeah,
it seems like it is adding more or like having less information. For example, when the representation size is 8,
yeah,
it also know there is a shell cap, but when you increase
Right.
the representation size, you kind of ignore it. That's
right. Yeah. So in a sense, that's actually a good thing here because the label that it's learned is to predict plastic bag. So this is just showing that I don't know. So like objectively, this may not be the right thing to you and I, but like the model has been trained with this kind of supervision. So it's sort of focusing on what it was trained to focus on, if that makes sense, instead of like what it should be, perhaps.
Regarding the size of the dimension, like the representation, I'm looking into like how that plays into the robustness of any classification task, for example, because
Yeah.
clean images we probably need a small dimension vector.
Yeah.
But as you have like common corruptions or even like adversarial coordination,
Yeah.
you might need bigger.
That's a great question. So we have a pretty, I don't know if it's in this this stuff. This is actually someone asked about like freezing non-linearities. This is the kind of numbers that we got for doing that. So if you don't freeze any of the backbone, you only get 5% accuracy with 8 dimensions. So you need to unfreeze a reasonable amount of the backbone to get performance. This is so that I don't know if I have the robustness results in this presentation, but we did do a bunch of experiments on robustness for these sort of ImageNet data sets out of distribution, ImageNet R, ImageNet O, all of these kinds of different kinds of corruptions. And so we have a little bit more analysis on that in the paper. So we do MRL does do reasonably well on robustness, but not, it wasn't optimized to handle that. So it just does sort of reasonably well.
But I mean, did you think about like, can you like train it specifically?
Yes. Yeah. So that's a great question. So one thing is that here, where is this? Right here. So these losses here, right now, these are all just the same loss, all cross entropy loss, just added together. But potentially an interesting thing you could do is to say, I don't really care about cross entropy. I want my 8 dimensions, my lowest dimensionality to do good at recall. So for a retrieval pipeline, for example, and instead of robustness. And I want, say, 2048 to do well on robustness. So if I want, depending on what task I actually want, I can, again, make a choice of what embedding size I need. But the only thing is that you would need some kind of proxy robustness loss or proxy recall loss because those things aren't, recall is not differentiable, so sadly, so you have to do these like proxy things. But there is some interesting works on using RL, for example, to learn like these kind of proxy like differentiable reward kind of things to learn these.
But if you're going to use let's say different losses or different tasks,
Yeah.
different sizes,
Yeah.
you probably need them to be compatible.
Yeah, we haven't actually done that, but that's an open question right now, is to see how would that even work, But it's super interesting. It's something we definitely thought of. It's just all of the work here is like we didn't know, we were just not bothered by trying to figure out like different hyperparameters, different kinds of losses. We just did the same exact setup as the default and said, okay, this works, and everything after that is just more sort of experimentation and playing around. Yeah, but it's a great question though. Yeah.
Do you find that like fine-tuning different parts of in terms of backing whatever fine-tuning network that fully fine-tuning always works like that?
Okay, sorry, can you repeat? If you fully find like if you
For the example, if you get a pre-trained model and you want to find either some layers or fully fine-tune, that fully fine always works like that.
Oh, I see what you mean. I don't know. I don't know if I would say always. But it typically works, but I mean, it works much better than if you just unfreeze like just the projection. Like just the projection does okay at like once you hit like maybe 128 or 256, but like below that it really drops off because it gets too small to optimize well. So you end up having to like unfreeze a bunch of the like the thing in the top of the table is like these like 4.2 conv3 conv2 whatever, these are just the layers of ResNet that I'm unfreezing to let gradients propagate while fine-tuning. So we also have experiments where we just fully fine-tuned. I don't think it's in this presentation, but it's in the paper. So we didn't see like how much of it you need to unfreeze until you get good. I don't know if it's the whole network, but it's definitely more than just here, more than just the last like the last layer.
Yeah, it will be a smooth curve at some point.
Yeah, you
See,
exactly. Yeah, yeah. I'm not sure exactly where, but there probably will be something like that. Yeah, yeah. I think we're at time, right? So
Sorry, one more question.
yeah.
So not sure if I missed this, but did you have any results where you looked at the performance if you only trained with a subset of the granularity? So instead of going all the way to 8, if you stopped at, let's say, 32, did the larger granularities have a higher performance than if you had included all the way down to 8?
We did do ablations to like see, instead of doing logarithmic, what if you do like linear granularity? So you do like 8 and then 256 and then 512 and then, you know, stuff like that. That worked pretty poorly because there's just not enough supervision at lower dimensionalities. I don't think we tried only lower ones because then the 2048 one would be garbage because it has no supervision. It's not encouraged at all to like learn good representations.
Oh, sorry,
But
no, you keep the 2048 all the way
right.
down to say 32, and you
I
don't,
see.
8.
I mean, my intuition is that it just wouldn't scale super well in the middle. Like it would probably drop off a little bit more if you go to like 1,000 or something, and then recover by the time it gets back to 2048. That's my intuition. I don't think that we actually ran that experiment, but we do have some experiments where we like optimized over different different granularities in the appendix of the paper.
Okay.
Yeah. Good. It's a good question though. Yeah.
There is no other questions. Let's thank the speaker again for this great talk.
Thanks, everyone.
Thank you for everyone to come.